Today we're going to talk about production and perception of sound. So you should have a handout that goes along with these notes, titled the same as these notes. You'll need it to quickly take notes while you go through this video. If you don't have the handout, please get it and return to watch the video after you have it. Otherwise, you're going to be doing a lot of pausing during the video in order to have enough time to take notes. So save yourself some time and get the handout. Okay. So first of all, we're going to listen to some sounds. Okay. So just take a listen. Okay, you don't necessarily have to close your eyes as you're watching the video because you're not going to be able to see what it is anyway. So here's the first sound. Try and guess what you think it is, and go ahead and write down what you think sound one is. Okay, so that was sound one. Okay, what do you think that was? All right, so now sound two. Okay, so what do you think that was? Okay, and then sound three. I know for me, a lot of times this sound is then accompanied by this sound. All right, so sound four. Okay, so write down what you think sound four was. Now for sound five. And I'll replay that one. Okay, so think about what that sound was. And then sound six. And I'll replay that one as well. Okay, so think about what that one was. And then sound seven. Okay, so let's see how you did. So sound one, you should have said that it was a telephone ringing. Sound two was a doorbell. Sound three was a dog barking. Sound four was like a thunderstorm with some rain. Five was rolling dice. Six was a stapler, like using a stapler. And seven was fireworks. So how did you do? Okay, and how are you able to identify the sounds while not seeing what produced them? Well, we use a combination of ears and mind that allows us to interpret sound waves and gain information. Okay. So direction of sounds. So I want you to have someone nearby toss something while you have your eyes closed. So like you close your eyes and they toss a coin somewhere around the room. Okay. Have them do this. And then I want you to then open your eyes after they've tossed it and see if you were right about where the noise came from. Like, where did it land when they tossed it? How can you tell the direction of a sound even though you're not looking at it? Like, you can't see it. Okay. Well, there's a number of clues, but a dominant clue is the difference in sound intensity and time delay between the ear signals. So a dominant clue is the difference in sound intensity and time delay between the ear signals. Okay, so with that in mind, could a person with only one ear tell the direction as well? The answer is no. Okay, a person with only one ear would not be able to distinguish the direction of sounds as well. Would not be able to tell the direction of sounds as well. Okay. So speaking of direction of sounds, let's look into that more in depth. Okay. There's this phenomenon called the Doppler effect. Okay. So I'm going to play something, and I just want you to listen. And I want you to see if you can figure out what it is. Okay, so what was the source of that sound? Well, it was a plane. And why does the pitch vary? Like, why does it get higher and then lower? What's happening? Okay, what's happening is this. So the plane's getting closer and then it's getting farther away again. So as it's getting closer, that's where the pitch is increasing. And as it's getting farther away, that's where the pitch is decreasing. So if a sound is getting closer to you, either because its source is approaching you or because you are going towards the source, the sound will seem higher than it really is. If you are heading away from a source, or it is going away from you, the sound would seem lower than its actual pitch. Okay, so if it's getting closer to you or you're getting closer to it, the pitch is going to seem higher. If you're heading away from a source or the source is heading away from you, the sound would seem lower than its actual pitch. Okay, so the Doppler effect happens because distance affects the amount of time it takes you to hear the sound. So if you hear a frequency in a shorter amount of time, you hear a frequency in a shorter amount of time, it seems like you are hearing a higher frequency. Okay, so let's see what that looks like. So I have here a simulation of a wavefront, and we're going to vary the speed of the source and observe the effect on the wavelength. So I'm going to click play. You can see how in the front here, the waves kind of pile up, and in the back, the waves are spread out. So let's show that again. I'm going to pause it so you can see how in the front of the wave, the wavelengths, the waves are very close together. So you have very short wavelengths and you have high frequency. So that's why it sounds higher pitched if something is approaching you. And then behind the source of the wave, you have longer wavelength and lower frequency, which is why it sounds lower pitched. Okay, then I'm gonna, just for fun, I'm gonna increase it because the speed of the source here is 80. The speed of the wave is 80. So I'm gonna increase the speed of the source to just a bit above the speed of the wave. So meaning it's just staying in front of the wave and it makes this cone-like shape. Okay, I'll show you again if you go a little bit more than that. You can really see the cone, right? Do you know what that's called? You might not yet, but you will soon. All right. So this is a simulation I just showed you. Okay. So what does this simulation show? Well, it shows that the shorter the wavelengths, the shorter the wavelengths, and higher frequencies for the observer as the sound source approaches and a lower frequency as it recedes or it gets farther away. Okay, so shorter wavelengths and higher frequency for the observer as the sound source approaches and a lower frequency as it recedes. Okay, so now let's talk about a sonic boom. Right, I'm going to show you a little video, and there's some information, like you have a little bit of room to make notes on your observations from the video, and there's also some things that you can fill in from the video. Like basically the rest of this part of the page is for this video. So let's watch it.
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes you can almost see it. Going close to that speed through air can cause some unusual visual effects. What you're looking at here is a NASA image of an SR-71 bending light waves from the pressure differentials it's producing. Air's pressure and temperature both drop when airspeed increases. Rapid changes in density can be enough to bend light like a lens. How does it happen? Airspeed increases as it flows over the form of an aircraft pushing its way near Mach 1, the speed of sound. That means that even aircraft slower than the speed of sound can accelerate the air moving over them beyond the speed of sound. As pressure all around the aircraft drops, that air cools. And as air cools, its ability to hold moisture drops. So if there's enough moisture, you'll see it form in clouds that appear attached to the aircraft itself. But the cone-shaped clouds you see aren't in fact traveling with the aircraft. Each section of air is spontaneously reacting to the temperature and pressure change induced by the aircraft's body sliding past. Then there are the shock waves. Shock waves are formed by the air that can't get out of the way fast enough, forming a pressure wave. We perceive that pressure wave as sound. Aircraft actually usually produce two booms. They just reach us so quickly in succession that we can't distinguish the two. All of these factors are quite normal and have come to be expected in images that capture supersonic, transonic, or even near supersonic flight. But on rare occasions, we do get a glimpse of something special. At Kennedy Space Center on February 11, 2010, an Atlas rocket launched into ideal conditions for showing off shockwave. And this is the result. We hope you've enjoyed this little tour of visual and auditory speed of sound phenomena. Visit avweb.com for aviation news and inside information for pilots. This has been Glenn Pugh for avweb.com. Thanks for watching.
Okay, so let's see how well you did listening during that video. So the speed of sound is about how many miles per hour? Well, if you listened in the video, it said it was about 760 miles per hour, or 340 meters per second on an average day at sea level. Okay. So a sonic boom is a loud, explosive noise caused by the shock wave from an aircraft traveling faster than the speed of sound. So it's a loud, explosive noise caused by the shock wave from an aircraft traveling faster than the speed of sound. Okay, and then shock waves are formed by air that can't get out of the way fast enough, forming a pressure wave that we perceive as sound. So shock waves are formed by air that can't get out of the way fast enough, forming a pressure wave that we perceive as sound. Okay, so that's sonic booms and shock waves. Then why did the cloud form behind the jet? Okay, so it forms a cone-shaped area of suddenly decreasing pressure. And this sudden drop in pressure cools the air. If enough moisture is in the air, a cloud forms as the air cools. Okay, and keep in mind that the lack of a cloud does not mean it didn't break the sound barrier. So I'll give you a moment to jot that information down. Okay, so let's move on. So audio signals describe pressure variations on the ear that are perceived as sound. Okay, we're going to focus on the periodic audio signals, or tones. And perceptually, tone separated by an octave, right, or a factor of 2 in frequency, that's what an octave is, are very similar. So like they're going to be very hard to tell apart. Okay, so destructive interference. Okay, we've talked about interference a little bit, just a little bit, but interference is very important to understand. So destructive interference is a type of interference that occurs at any location along the medium where the 2 interfering waves have a displacement in the opposite direction. Okay, so it's where the 2 interfering waves have a displacement in the opposite direction. Okay, and this just shows you that before the interference, after the they each, like, you have crest and you have trough. During the interference, the red crest lines up with the blue trough and they cancel each other out to where it has no amplitude. Now, after they pass, they continue to have blue will continue to on its way just like it was before, and red will continue on its way just like it was before. To show you that, okay, this little simulation. Scroll down to destructive interference. Let me play this for you. Right. So these top 2 waves, that's showing like your wave 1, wave 2, and then the sum of the waves is this 3rd wave down here. So I'm going to play that again so you can watch it. Okay, notice how they just pass right through each other and they continue on how they were before. Okay, so when one crest and one trough arrive at the same time and cancel each other out, if they are identical in size. Now, this is a temporary canceling out. This is a temporary thing. Okay, so when one crest and one trough arrive at the same time and cancel each other out if they are identical in size. And this is a temporary thing, right? And you can have partially destructive waves that may not cancel each other, but dampen the wave temporarily. Remember, dampen means that you're going to decrease the amplitude, okay? And that's what I showed you in that little simulation, this right here. It's not completely canceling each other out. It's just dampening the wave when they cross, okay? So this shows you, you know, before they cross, when they cross, they cancel each other out, and then after they pass one another, they're back to normal. So constructive interference is a type of interference that occurs at any location along the medium where the two interfering waves have a displacement in the same direction. Okay, where the two interfering waves have a displacement in the same direction. Okay, so that might be like two crests or two troughs. Okay, and again, the interference is temporary, right? And the two crests or the two troughs would make a larger wave. And again, that's a temporary larger wave, right? And this diagram shows you before the interference, you have your two crests approaching. Whenever they come into contact, they're going to overlap and produce a bigger wave. Let me show you what that looks like in a simulation here. Okay, so this is constructive interference. Top two waves are the individual waves, and then the bottom one is the sum of the waves. So I'll show that again. So notice when they cross, that's where the wave gets much larger. And again, it is temporary. Okay. So waves coming into contact, they get much bigger, all right, when they cross, and then go back to normal after they cross, right? How we determine how big a wave gets or how small a wave gets through interference is determined by the principle of superposition. So we use the principle of superposition to determine the shape of the resultant waves during interference. So the principle of superposition states when two waves interfere, the resulting displacement of the medium at any location is the algebraic sum of the displacements and the individual waves at that same location. Okay, so the resulting displacement of the medium at any location is the algebraic sum of the displacements of the individual waves at the same location. Okay, so let's look at what that means. So a crest is kind of like positive and a trough is negative. So waves do not change shape or size when they meet. They can pass through each other. However, when they overlap, a different shape wave emerges temporarily. So you might want to underline temporarily. And then this little diagram here, which you do have on your handout, has that the amplitude of A, right, where you have a crest, minus the amplitude of B, where you have a trough, will give you the amplitude of C, which would be your resultant amplitude for the waves when they're in the same point in time. So let's say amplitude A is 10 centimeters, amplitude B is 5 centimeters. That means you would have a resulting amplitude of 10 minus 5, which is 5 centimeters. Okay, so that's how you determine the size of the wave. Okay. So now let's put this interference to use, right? Sound wave interference and beats. Okay. So I'm going to play you a sound. Okay. Do you hear one tone or two when you listen to that? One tone or two. And then I'm going to play this one. And again, you're going to be listening to one tone or two. That's what you're deciding. Okay. So can you hear two different tones? Do you hear the beats, basically where it kind of trills a little bit? Okay. So whenever you have two similar frequencies, that's what produces beats. Okay, so two similar frequencies produce beats because they spend a little while in phase and a little while out of phase. So they spend a little while in phase and a little while out of phase. Okay, and the result is beating of sound amplitude. Okay, so you can see here, when they're in phase, they're going to add, right? So whenever you have, two crests lining up, they're going to add together to make a larger wave. Whenever you have a trough and a crest lined up, they're going to cancel each other out, at least partially, and you're going to get beats. Okay? So beats are the periodic and repeating fluctuations heard in the intensity of a sound when two sound waves of very similar frequencies interfere with one another. Okay. So then this diagram here shows how you get beats a little better. So the red wave and the blue wave are going to interfere with one another. And you have areas of constructive interference, which is going to produce larger waves. And you have areas of destructive interference, which are going to produce smaller waves. And so this green wave is your beat. Okay. So some vocabulary, because we have some terms that mean very similar things. So if you have sound quality or timbre, that describes those characteristics of a sound which allow the ear to distinguish sounds which have the same pitch and loudness. So it's what allows you to distinguish like the same frequency being played on a piano versus being played on a violin. Okay, so timbre is then a general term for the distinguishable characteristics of a tone. Okay, so it's what makes like a piano tone, like how we know it's a piano and not a violin. And then pitch is just another way to say frequency. Okay, it's the highness or lowness of the sound. If you hear something with a higher pitch, then you hear it as a louder sound. Okay, so the pitch is the frequency of sound. So it's how high or low it is. Okay. So intensity and the decibel scale. So the amount of energy, because remember sound waves transport energy, the amount of energy that's transported past a given area of the medium per unit of time is known as the intensity of the sound wave. And the greater the amplitude, the greater the rate at which energy is transported, and the more intense the sound wave is. Right? So basically, you turn up your volume, more energy is going to be transmitted, it's going to sound more intense. Right? And intensity is equal to power divided by area. The units for intensity are watts, remember units for power are watts, divided by your units for area, which are meters squared. Okay. Oops. The intensity of a sound wave decreases with increasing distance from the source. Okay, and that makes sense. If you get farther away from a speaker, it sounds less loud, it sounds less intense. So the technical mathematical relationship is this. The intensity varies inversely with the square of the distance from the source. So the intensity varies inversely with the square of the distance from the source. So the faintest sound that a human ear can detect is known as the threshold of hearing. Threshold of hearing. Sorry, that was my dog. He has a higher threshold of hearing than we do. And the threshold of hearing for humans is equal to 1 times 10 to the negative 12 watts per meter squared. Okay. So the range of intensities that the human ear can detect is very large. So to account for that, we use a logarithmic scale. Okay. The scale for measuring intensity is called the decibel scale. Right? It's called the decibel scale. Ten times more power represents 1 bell or 10 decibels. Remember, deci, the prefix deci means 10. Like a decimeter is a tenth of a meter. Okay. So 1 bell or 10 decibels more intensity. To figure the ratio of intensities, you should use the number of bell units placed as the power of 10. So in this way, 10 decibels or 1 bell represents a 10 to the 1 ratio. 20 decibels is 2 bells and represents a ratio of 10 to the second, which is 100. Okay. represents a 10:1 ratio. And then a 20 decibel is 2 bells and represents a ratio of 10 to the second, which equals 100 times more intensity. Okay, so an example. On the front row of a concert, the sound level reaches a value of 100 decibels. In the back row, the sound intensity is reduced by a factor of 10,000. What is the decibel level on the back row? All right. Well, 10,000 is 10 to the 4th because you have 4 zeros. So this is equal to 4 bells or 40 decibels. So then we can take the starting amount of decibels of 100 at the front row and subtract 40 decibels, which is how much it changes by, and that will give us what the decibel level is on the back row, and that will be 60 decibels on the back row. Okay. So the threshold of hearing is assigned as a sound level of 0 decibels on the decibel scale. Okay. Sustained sound at 110 decibels can cause hearing loss. And you can tell if the sound is loud enough to cause hearing loss because it will make your ears actually ring. Okay. So here's a little hearing test. Okay. Which apparently it needs to load. All right. So I'm going to select some tones. Hopefully you'll be able to hear them. Depends on how good your hearing is. So let's pick, oh, that's too low. Let's pick something a little better. Okay. 375 hertz. 500 hertz. So 375 hertz. And that's at, let's play that at 30 decibels. Okay. And then let's play it again. Okay. So with those tones, all right, as you got about 10 decibels difference, you could really tell how much louder it was. And so on average, a 10 decibel difference should be perceived as twice as loud. Does that mean that it is for everyone? No. Everyone has different hearing. In fact, you have different hearing as you age. So let me show you what I mean. So as you get older, all of those, like at each of the age levels, it just all kind of sounds the same. Like a coworker of mine, he's a bit older than me, he says that they all sound the same. He can't tell the difference as the sound gets softer and softer for each age group. Right. So now what you're going to do, you should have the sound questions, right? And you're going to complete that. Anything you don't finish in class, which I guess if you're watching this video, you weren't in class, those sound questions are homework, right? You have a long weekend to do them, and they are due on Monday. No exceptions. Our test over all this material is on Tuesday, April 3rd. So no use procrastinating doing these sound questions. Get them done. All right. Just a hint for numbers 2, 3, and 5, you don't need to calculate the answer. It's just telling whether you will hear the sound at a higher or lower pitch and why. So hint, hint, Doppler effect, right? So the Doppler effect will help you with 2, 3, and 5. And you can work with your table mates. You can work with a partner in the time that remains in class. Again, if you're watching this, you're not in class, so that doesn't really apply to you. It's solo work at this point. And you can also use the decibel scale handout and the notes over resonance from last week, in addition to the notes from today for help. Okay, hope this helps you complete your sound questions, and hope you learned something new. Have a good day.